Here are the sample problems for Math 117, Class 18, in which you'll meet some unexpected martingales. So for the first one, let's consider a symmetric random walk. Symmetric just means the probability of going up or down, left or right if you prefer, is 50% in either direction, but we can start anywhere that we want. So let's start at y equals 1. That's step n equals 0. And then we can take a step in either direction, either up to 2 or down to 0. And to get to n equals 2, again, we can step up to 3, or we can step down to 1. And from 0, we can step up to 1, or we can step down to -1. Now, what's surprising about this is not only that y sub n is a martingale, but also the new random variable, which I'll call z sub n, y sub n squared minus n, is a martingale. So let's write in the values of that. That's 1 squared minus 0. Here we have 2 squared minus 1 and 0 squared minus 1. And at n equals 2, we have 3 squared minus 2, or 7, 1 squared minus 2, or -1, and -1 squared minus 2, also -1. What we have to show is that the expectation of this martingale, and I'm going to do it for the step from 2 to 1, so I need to show that the expectation of z2 conditioned on the value of y at 1 is equal to z1. Notice it's not sufficient to show that the expectation of z2 is equal to the expectation of z1. That's a necessary condition for a martingale, but not a sufficient one. We have to check this for two specific cases. So let's first check the case where y1 of omega equals 2. So we consider all the paths that go through that node. Denise would want me to say that I'm conditioning on a sigma field, but the sigma field is just the one generated by the partition following from the different values of y here, 0 and 2. Most people are sloppy and just say they're conditioning on a random variable. Okay, what's happening here? Well, first let's work out z1. z1 is equal to 3. And then let's calculate the expectation of z2 conditioned on y1 being 2. In that case, we're either going to go up or down, and we have 1/2 times 7 plus -1, or 3. Now, notice what we're confirming here is that two random variables are equal. So we also have to check the case where y1 on a specific omega in the sample space is equal to 0. Notice we only have to check this, although it's a random variable, for one omega that hits this node and one omega that hits that node. Okay, in this case, z1 is equal to -1, and the expectation of z2 conditioned on y1 being equal to 1 is 1/2. Well, it's -1 in both cases, so everything checks. But you don't want to do every case, so let's figure out how we can do this in the general case. Let's suppose that yn has a value that we'll call m, and in that case z sub n, of course, will equal m squared minus n. And now I have to work out the expectation of z sub n plus 1 conditioned on yn being equal to m. In other words, we can either go up to m plus 1 or down to n minus 1. Each of those will happen with a probability of 1/2. So if we go up, the new value of z is m plus 1 squared minus n plus 1. If we go down, the new value is, of course, m minus 1 squared minus quantity n minus 1. What's that? Well, that's 1/2 m squared plus 2m plus 1 minus n minus 1 plus 2 plus m squared minus 2m plus 1 minus n minus 1. And things cancel like crazy. That cancels that. That cancels that. That cancels that. And what do we get? We got 1/2 of 2m squared minus 2n, or m squared minus n, which checks. So that's one way to do it. Here's a more elegant way. We'll use the conditional expectation rules. We're trying to calculate the expectation of z sub n plus 1. Well, that's the value of y at n plus the random variable x n plus 1. That is equal to plus 1 if we step up, minus 1 if we step down, minus n plus 1, and this is conditioned on y sub n. Now we exploit the linearity of expectation. Multiplying out the square, we've got expectation of yn squared conditioned on yn plus 2 times the expectation of yn times xn plus 1 conditioned on yn plus the expectation of xn plus 1 squared conditioned on yn. And I'm sure you'll believe me when I assert that the expectation of n plus 1 conditioned on yn is n plus 1. Okay. Now, let's use our rules. Taking out what is known, yn squared is certainly constant on any specific value of y sub n, so that's just y sub n squared. Here, we've got a product of two random variables, and one of them is constant on the values of y sub n, so we can pull that out. So I get 2 times y sub n times the expectation of x sub n plus 1 conditioned on y sub n plus, well, xn plus 1 is independent of y sub n. We're equally likely to go up or down independent of the value of y, so this is just 1. And we're almost done. Here, I can say again, independence drops out. we get 0 plus 1 minus n minus 1. We get y sub n squared minus n, which is z sub n, and everything checks. Well, you're saying, for a symmetric random walk, we clearly have a martingale, but if the probability of going up is different from the probability of going down, we don't have a martingale anymore. Well, not if you use the location as the random variable, but Abraham Dumas some centuries ago figured out how to make a martingale out of this. So here's the storyline. They're opening up a new casino in Everett, Massachusetts. Suppose you go there, you walk up to the second floor, and you say, I'm done of walking. This place has to have elevators. And you discover that the elevators are a real gamble. Inside the elevator cabin is a button marked Go, and when you press it, you've got a probability 1/3 of going up a floor, a probability 2/3 of going down a floor. So let's draw a diagram for this. You start at y equals 2, and in n equals 1, you can either go up to y equals 3 or down to y equals 1, but you go up with a probability of 1/3, down with a probability of 2/3. Again, when n equals 2, if you're already on the third floor, you've got a probability of 1/3 of going to the fourth floor, or you may get back to the second floor with a probability of 2/3. And if you say, this is looking awfully much like those scratch tickets, well, that's what we're planning to apply the theory of martingales to. Okay, now, here is the remarkable martingale. Z sub n equals 2 to the y sub n. So, here we have z0 equals 4. Here we have 2 cubed, so z1 equals 8, or z1 equals 2. Here we have z2 equals 16, or z2 equals 4, or z2 equals not 0. We're on the 0th floor, but 2 to the 0 is equal to 1. It's clear that yn is not a martingale because y0 is equal to 2, while the expectation of y1 conditioned on y0 is 1/3 times 3 plus 2/3 times 1, which is equal to 5/3, which is not equal to 2. But let's try z. We're going from 0 to 1. We've already figured out that z0 equals 4, and the expectation of z1, I'll write down I'm conditioning it on z0, but z0 is the only possibility, so I'm conditioning on the entire sample space. What do I have? 1/3 for what happens when I go up, plus 2/3 for what happens when I go down. That's 8/3 plus 4/3, which is 4, which is just fine. And going from 1 to 2, now I've got to be a little bit more careful because remember, I'm trying to prove the equality of two random variables, and I have to consider one omega that goes through that node, another omega that goes through that node. So we'll have y1 equals 3. In that case, z1 equals 8, and the expectation of z2 conditioned on y1 equals 3 is 2/3 for going up to 16 plus 1/3 for going down to where z equals 4. That's equal to sure, I got this backwards. 1/3 for going to where z is 16, 2/3 for where it's going to 8. That's 16 plus 8, or 24 over 3, which is equal to 8. But I have to check again for the other case where z1 is equal to 2. And I compare that with the conditional expectation of z2 conditioned on y1 being equal to 1. In that case, we have a third probability of going up to the second floor where z equals 4, 2/3 for going down to the ground floor where it's equal to 1, and what do you know? That's 2. Well, let's see if we can do this in general. So we're going from n to n plus 1 with y sub n is equal to m, so that z sub n is equal to 2 to the m. And all we have to do is compute the conditional expectation of z sub n sub 1 conditioned on being in state m for yn. So we've got a 1/3 probability that m will increase, in which case z goes up to 2 to the m plus 1. We've got a 2/3 probability of going down to where y equals m minus 1 and z equals 2 to the m minus 1. And we've got a nice common factor of 2 to the m. In the first term, we have an extra 2 over 3. In the second term, we have 2/3 times 1 over 2. That's 2/3 plus 1/3, multiplying 2 to the m. That's equal to 2 to the m. And that actually establishes that it's a martingale just as quickly as any of my sample numerical calculations. Credit for this goes to Abraham Demoivre, 1667 to 1754. He's most famous for his theorem involving trigonometric functions, sines and cosines of multiple angles, but he was one of the pioneers in the mathematical study of gambling. Well, I just realized I neglected to advance the page on the previous problem, but I'm not going to go back and redo this recording. Sorry about that. Now we're on page 3, and this is another very famous martingale. This is the subject of an article I wrote a couple of years ago on single-gender social organizations, and I put a link to that on the course website. Here's another storyline for it. House of Representatives is setting up a new committee to explore the possibility of sponsoring gambling in the hopes of reducing the national debt. And they start out this committee small, 1 Democrat, 1 Republican. And the way it's going to grow is a member is chosen at random to add a new member for the committee. A Democrat always picks a Democrat, a Republican always picks a Republican, and this process just keeps going. So d sub n is now a random variable. After we have added n members, it's the total number of Democrats, and what I'm going to show is that the fraction of Democrats on the committee, which is d sub n over the total committee membership, it started at 2 and we added n new members to show that the proportion of Democrats is a martingale. Let me first do an example. Going from n equals 1 to n equals 2. Okay? There are 2 cases. first case is that there's just one Democrat on the committee after we've added a member. That means we have one Democrat and two Republicans. Then D2 can remain 1, and it will happen with probability 2/3, because 2/3 of the committee is Republican, or D2 can become equal to 2 because the Democrat got to pick the new member. Okay, what do we have to check? We have to look at Y1, which is equal to 1/3, and compare that with the expectation of Y2 conditioned on D1 equals 1. Only one Democrat. So we've got a probability of 2/3 that we still have only one Democrat, and the committee consists of one Democrat out of 4 members. We do have a probability of 1/3 that we pick another Democrat, and we get 2 out of 4. That's a 6th plus a 6th, which is equal to 1/3, which checks. The other possibility is D1 equals 2. That means we've got 2 Democrats and 1 Republican. In that case, we've got a probability of 2/3 for a new Democratic member, 1/3 for a new Republican member. And we do the martingale check. The value of Y1 in this case is 2/3, while the expectation of Y2 conditioned on the value of D2 being equal to 2 is a probability of 1/3. Since the Democrats are now 2/3 of the committee, the Republicans have only a 1/3 chance of picking the new member. In that case, there will be 2 Democrats out of 4. There's a 2/3 probability that the Democrats get to pick the new member, in which case there are 3 Democrats out of 4, so the proportion of Democrats is a 6th plus a half, which is equal to 2/3. Of course, special cases prove nothing, so let's consider the general case. We're going from n to n plus 1 with n Democrats on the committee. In other words, the value of y sub n is m over n plus 2. Well, as with the previous cases, doing the general calculation is just about as easy as doing a numerical example. Okay, we've got m Democrats out of n plus 2 members, so that's the probability that the Democrats get to pick the new member, in which case there are m plus 1 Democrats out of n plus 3 members, or one of the n plus 2 minus m Republicans out of n plus 2 members gets to pick the new member, in which case there are still m Democrats, but now out of n plus 2 members. So we've got 1 over n plus 2 times n plus 3 multiplied by m times m plus 1 plus n plus 2 times m minus m squared. Nice to see that go. And what do you know? We've got n plus 3 times m. So we've got m times n plus 3 over n plus 2 times n plus 3. That cancels, and everything checks. This one was discovered or publicized at least. Somebody must have stumbled across this before, by the great mathematician Gor Polya and his collaborator Eggenberger, whose name I'm not going to take the time to write, in 1923. Polya's version of the problem was you don't have Democrats and Republicans, you've got black and red balls in the urn. And pick a ball, put it back, and add another one of the color that you drew. So this is now known as the Polya's urn martingale, and there is, in fact, an entire book that's now been published that's devoted to it. So there's your nice introduction to martingales.